Welcome to Thursday. I know it feels like a Tuesday, but it's a Thursday. Thursday all day until tomorrow. Friday. Wow, 3-day week. I can do this all the time. All right, so today, before we introduce our guest for today, I just want to remind you that next week will be so, we are in October 4. Yep. Okay. We also have coming up this month Steve Armstrong. We'll be talking about taxicab geometry. It's going to be pretty cool. And in November, we have a number of patent law type science seminars and another one on modeling of materials. And in December, we'll be finishing out with some X-ray crystallography and molecular biology. So lots of good stuff coming at this semester for science seminars. But before all of that, we have today's speakers. We have Dr. Hathaway, who will be introducing our speakers for us today. So let's give Dr. Hathaway.
Thank you all for coming today. We enjoy the opportunity we have. And we're going to talk about research that we've done in our lab for a while. And basically it's over 3 generations, because Tyler is representing sort of the senior chemistry majors who worked on this. Jordan's representing the junior chemistry majors, and Priscilla's representing the sophomore chemistry majors. So the bottom line is students over a wide range of abilities and skills have worked on this. What I like to do in terms of research is sort of twofold. I like to design organic chemistry labs that make you think. Just converting X to Y is boring to me. You need to figure out what's going on. Why is it going on? Are we really making Y? And so I like to make our students think as they're doing the organic chemistry labs. A lot of times the clicker works. A lot of times the organic chemistry experiments have been published and we try them and they just don't work that well. And so, okay, this is a great idea, but how can we make it better? So I spend a lot of time trying to improve published organic experiments just to make them work better. And then the other part of my goal in research is design better antimicrobial drugs. Most antimicrobial drugs, penicillin, sulfonylamides, etc., have a lot of bacterial resistance. So trying to design new chemical entities that can overcome some of the resistance of these things. So, those are really the big research interests that I have. And actually what you're going to hear today combines these interests of mine. So Tyler and Jordan are going to be talking about work they've done on changing the structure of sulfonilamide to try to improve its antibacterial potency. Jordan's going to talk about work he's done on this end. Tyler's going to talk about work that's been done on this end. And some of this work was previously done by Organic Chemistry 2 students, Marissa Trozen, Sean Gowing, and Robert Moreland, who previously worked on some of these projects. Then Tyler and Priscilla are going to be talking about extracting spices using household kitchen appliances, which can be much faster than the traditional methods of doing these. And they're also building on work that Marissa Trozen, started off beforehand. Ask that you please hold your questions and applause until we've all finished speaking. That would just let everything flow faster. So to start us off, we have Jordan Chang.
Don't.
All right, good morning, everybody. So for those who don't know me, my name is Jordan Chang. I'm a junior studying chemistry with engineering concentration here at LeTourneau. And I did research over the summer here along with Dr. Hathaway, Priscilla, and Tyler. And I'll be sharing my experiences and process of making the sulfa drugs that I did over the summer, and I hope that you guys would enjoy it. So my part of the summer research involves in altering the N4-amine groups of sulfanilamide, which is shown in the PowerPoint, which is highlighted in blue. So what's so special about sulfanilamide and sulfa drugs in general? Before understanding sulfa drugs, we have to understand its structure first. So the structure of sulfa drugs or sulfanilamide has a general aromatic sulfatamide. So what it means that it has a sulfur that is double bonded to 2 oxygen atoms, and at the same time it's also bonded to 1 nitrogen atom, where the nitrogen atom can either be an amine, imine, or any kind of nitro groups. So sulfa drugs were the first chemical substances systematically used to treat and prevent bacterial infections for humans back in the 20th century. And the use of sulfa drugs has been diminished these days because of the availability of better antibiotics such as penicillin, which is more effective and safer to use for human consumption. Sulfanilamides are still used these days, but largely for specializing in treating urinary tract infections and infection of burns. So sulfatamides are first discovered in 1932 by German bacteriologists and pathologists named Gerhard Domach, which he noted the effects of red dye prontosol on streptococcus infections in mice. So it's later proved by French researchers that the active reagent of prontosol was sulfanilamide, or para-aminobenzene sulfatamide, which is a product of the body's metabolism of prontosol. Because of this, Gerhard Domach was awarded the 1939 Nobel Prize in Physiology and Medicine. By the 1940s, sulfanilamide was a widely used drug. During World War II, white sulfanilamide powders became a standard for first aid kits for the treatment of open wounds, and sulfanilamide tablets were taken into consumption to fight intestinal infections. Though the sulfa drugs were relatively safe, however, allergic reactions such as skin rashes, fever, nausea, vomiting, and even mental confusion were the common side effects for some people. Besides that, bacteria develop a type of resistant strains after a long time of exposure to the existing sulfa drugs. As such, within a few decades, many of the sulfa drugs has lost its favor to more effective and less toxic antibiotics. So as you can see in the picture shown, back in World War II, sulfanilamide powder were packed into sachets, and if a soldier got hurt during a battle, they would apply the powder onto their fresh wound to stop the bleeding and to prevent any type of bacterial growth. So back in World War I, more men were killed by bacterial infections than getting killed in the battle, and the invention of sulfa drugs was a really huge contribution towards World War II. So here's an outlook of the general scheme of what I did over the entire summer research. So mainly we're looking at 3 different types of parts of reaction schemes that we have here. So the first reaction, we have sulfanilamide as our starting material, and we would react it with any type of substituted benzaldehydes, and we would get the Schiff base or the imines. So the special characteristic of an imine or a Schiff base is that it has a nitrogen that is double bonded to a carbon. And for the second reaction, we would take the existing amine or the Schiff base created from the first reaction, and we would react it with zinc and ammonium formate to produce the reduced amine. So if you take a closer look, the reduced amine has only a single bond here, where before it was a double bond, so it is reduced. And the whole objective and the whole goal of this research is that we would like to find like a one-step synthesis where we can just take sulfanilamide and benzaldehyde, any type of substituted benzaldehyde, and just like react it with only one reaction to create the reduced amine version of it. So we begin our reaction with sulfanilamide as our starting material, and we react it with any type of benzaldehydes to produce the desired Schiff base or the imines as our product. We chose 1-propanol as our solvent because sulfanilamide dissolves really easily in 1-propanol. The reaction is heated under reflux averagely for about 2 hours, and depending on the aldehydes used. Glacial acetic acid is used as the catalyst to speed up and accelerate the formation of Schiff bases. Besides that, 2 to 3 amounts of aldehydes is used to force the equilibrium towards the formation of products. However, this becomes a problem later because the excess aldehydes that we added within the reaction mixture would make it more difficult to isolate the product that we want. So as such, each Schiff base were isolated through suction filtration and had to be washed and stirred under 95% ethanol or diethyl ether to remove the unwanted aldehydes. If we still can't remove all of the aldehydes, we would just perform a recrystallization procedure, which will force the product to form a pure product itself. So as you can see in the picture shown, this is an example of the Schiff-based solid product formed by reacting sulfanilamide with salicylaldehyde, which is a type of benzaldehyde that we use. The compound that has the most yield was the one that is trincinyl aldehyde, which gave us a yield of 95.95%. And the amine that gave us like the least yield was the one with O-anisaldehyd, where it only gives us about 36%. If you notice in the table shown, all of the Schiff bases compounds have a steep melting range. So what it means that the product that we got was pretty much pure. So if you have a really narrow melting range, it's pretty much pure. So before, Robert and Marisa tried using sodium borohydride as the reducing agent to reduce Schiff bases into sulfotamide amines, but it wasn't that effective and it didn't produce good yields. So we looked into the literature and found another method to reduce Schiff bases into amines. In the literature text, methanol was used as the solvent. However, we used 1,2-dimethoxyethane, which is also known as glyme, as our solvent, because most of the Schiff bases do not dissolve in methanol, but dissolve in glyme. The reaction is also heated in reflux to accelerate the formation of products. At the same time, excess amount of zinc and ammonium formate is also needed because ammonium formate periodically decomposes into ammonia gas and carbon dioxide gas throughout the reaction. Usually we would expect like a solid product form at the end. However, in our case, we had a really adhesive and viscous solution instead. This might be caused by some of the impurities that were present by any site reactions or something. Based on the NMR spectrum, we noticed like the imine peak at the 7.5 ppm region was gone. But at the same time, we had a couple of multiple unknown peaks, which also means that there are impurities in the product. So we also used thin layer chromatography, TLC, to further analyze the product. The TLC the TLC results showed us a couple of spots and unreacted starting material, which is not really what we want. So if we had more time, we would figure out a way to just remove all of the impurities and just to isolate the pure product that we want. So as I mentioned earlier, the big picture of the research is to come up with a one-step reductive amination synthesis from sulfanilamide and any type of aldehydes and directly convert it into the reduced amine Schiff base. Reduced amine. As such, we looked out into the literature and found a one-step synthesis to produce the reduced amine sulfotamide. In the literature text, 1,2-dichloroethane was used as the solvent for this reaction. However, in our case, DCE doesn't dissolve sulfanilamide, and we had to use tetrahydrofuran THF instead. 2 to 3 times the aldehyde and sodium triacetyl oxyborohydride was used in the reaction to force the equilibrium towards the formation of products, as usual. However, just like the problem that we had in the first reaction, the excess aldehydes present in our products form, it's not really good, and we had to wash it with 95% ethanol and recrystallize it. So the NMR data showed us the presence of aldehyde peaks, even though we have performed the washing and like the recrystallization. Besides that, the amine peak at the 7.5 ppm region is still present. That means that the product that we got is not really what we wanted. So research challenges. So the waiting time for some of the products took us about like 3 hours. Like for example, like the O-anisaldehyd reaction took us like 3 hours. So we just had to wait for the reaction to complete, and we had nothing to do while we were waiting for that reaction to happen. So like I said earlier, like the one-step synthesis product didn't give us the product that we desired. So if we had more time, we would pursue like another reductive amination procedure where we take sodium cyanoborohydride to reduce SR reducing agent instead. So the most difficult part of the research is to find the right TLC solvent to analyze the purity of products. So if you have taken general chemistry or organic chemistry, you would know that different compounds have like different polarity. So we had to spend like a significant amount of time to find like the right TLC solvent to give us like the best separation of spots for the TLC. So as I mentioned earlier, we added excess amount of aldehydes into most of our reactions to drive towards the equilibrium towards the products. So this causes us to take like the NMR spectrum really frequently to verify the desired organic structure of the products that we want. So an NMR spectrum would take about 15 to 20 minutes to take. And if we have like a bunch of like solid or product made, we have to take like a bunch of them, and that would waste a lot of time. So yeah. And right now, Tyler will be presenting his part on the N1 substituted sulfonamide derivatives. There we go.
Thank you. Hello guys, my name is Tyler Wormley. I am a chemistry major here with biological concentration. I am hopefully a senior, Lord willing. Now I'm going to be talking about the synthesis of N1 substituted sulfonamide derivatives. So on this side, whereas Jordan was just talking about modifying this side of the structure. What are we going to do? Well, we're going to try to remove chlorine right here, cleave it from the sulfur group, and then we're going to try to attach this aniline derivative onto there, and hopefully we'll get this product, and then later we'll do something else. How are we going to do it? We're going to combine anacetyl sulfonyl chloride, which is NaSC, substituted aniline acetonitrile, potassium carbonate to level the pH, and then heat it to reflux. Afterwards, we'll dilute it with water. We'll cool it and we'll acidify it with hydrochloric acid. This is so that the pH of the product is desired range, so we get the most product out. And then we'll suction filter to obtain the final product and wash it. Here's all the substituted anilines that I used, so all the compounds that I tried to attach. For example, there's 2-chloro, 3-chloro, 4-chloro, so you can see get an idea of what these will look like. Some of them are di-substituted, so this one has 2 groups on there rather than 1. So through step 1, we got pretty good results. All of the anilines did form a good product, so we got a product. Now, notice that the monohalogenated anilines, so these top 5 right here, produce the best yields. So that's just something cool to note. And compared to the difluoro compounds, they did not produce very good yields at all, and those are di-substituted halogenated compounds. And then the last step of this process is to cleave this acetyl group to form the product. Oops. I cleaved everything. So we're going to get rid of this group right here and attach an H, and then that'll be our final product, and hopefully the antimicrobial that we want. How are we going to do this? We're going to reflux the step 1 product with hydrochloric acid and ethanol for about 50 minutes to an hour. We'll dilute it with 20 mils of water in a beaker and then cool it in an ice bath to promote solidification. We'll add sodium bicarbonate until the precipitate forms and the pH is neutral. And then we'll collect the product through suction filtration and wash with water. Put it in the oven, and then check the stuff out later. The results from this step, the monohalogenated anilines produced the purest final products. So even though we got good % yields, that doesn't necessarily mean that these are pure. Now, the best yields came from the chloro and iota substituted, and those were also the best, or 2 of the top in the step 1 results. So that's interesting. And after further analysis of IR and NMR, both of these difluoro compounds produced these really weird peaks. Couldn't really tell what they were, so I think they're salts probably, which means they're kind of nothing. In conclusion, monohalogenated anilines in general produced the highest amount of yield. Further biological testing would have to be done if we want to see if these are actually good antimicrobial drugs or antibiotics. The reported method of substituting anilines on NaSC did not work very well in our favor. It talked about using pyridine and It didn't talk about heating to reflux, so you could just leave this reaction stirring overnight, which takes forever. So we made some changes there. And then solidification of product at pH range 7 was pretty sensitive because some products would want to be at pH around 7, some would want to be around a pH about 9, and you couldn't really tell. So if you went over the pH range or stayed under, then you can't really go back, you wouldn't get that product back, you just lose it. And now we're going to talk about the second part of my research. This is what I did last semester, and it's the extraction of essential oils from cloves using an espresso machine, Keurig machine, and an AeroPress. So probably what a lot of you guys use. Why are we going to do this? Because essential oils are used for a variety of medicinal and aromatic applications. Normal extraction involves steam distillation, which takes like forever, like 4 hours or more sometimes. And whereas this method will take like 15, 20, 30 minutes. We're going to take about 12 grams of the ground spice, so in my case I did cloves. We're going to put it in the portafilter or K-cup, and then we'll fill the reservoirs of the machines up with 25% ethanol, 75% water. We'll collect about 200 mils of extract from both machines, and then we'll extract these with hexanes and then evaporate the hexanes off, so then we're left with just our essential oil. Marissa Trosten did this before me. She ran one trial on 4 different spices: cloves, star anise, caraway, cinnamon bark. And these are the results she got. Steam distillation produced the most, with espresso behind, and Keurig produced some as well. And I was looking at these and I saw that, I mean, you only got about half out of the espresso and Keurig compared to steam distillation methods. Well, she only did one trial. So I decided I'm going to do more than one trial, see if I can't get the most out of the stuff that I can. So we did that, and I did 5 extractions of cloves through each of the machines. Espresso method yielded the most product, and as you can see, most of the product was found in these first 3 trials, and the last 2 extractions aren't really necessary. Questions at the end. Thank you. In conclusion, the espresso machine is the most effective method of extracting cloves and essential oils from the cloves, followed by the Keurig, and then the AeroPress, which an AeroPress you have to actually physically like push on it, so that was kind of hard. Majority of the clove oil is extracted within the first 3 extractions, and the hardest part of this research was getting the consistency of the grinded material right. So if it was too fine, there wouldn't be enough solution coming out. If it was too coarse, there'd be too much, and it wouldn't be very strong. So it was hard figuring out how to get the grinded consistency of the cloves. And now Priscilla's going to talk about hers.
Which button? Okay. I'm Priscilla. I'm a second year chemistry with biological concentration here at Laterno, and I'm basically the 3rd leg of the PHWE and SPICE research team. So just taking a step back, I want to explain like what an extraction is in its most simple form. You can think of it like you're making tea. You take a natural product, you put it in a hot solvent, and you let the organic molecules of the natural product kind of diffuse into the solvent, and that whole process right there is the extraction. And then afterwards, what do you do when you drink tea? You drink the water. So what we want is the extract that we have in our solvent, and then we're going further with that. We're quantifying our results. Basically, we're controlling how much spice we're using in our experiments. We're controlling how much solvent we're using. So that then we can actually measure out how much of our oil is actually in the solvent that we're getting out in the tank. There are 2 different ways to do this. You use steam distillation methods or PHWE methods. Everyone has pretty much seen, if you take in General Chemistry 1 here, a mini type simplified steam distillation apparatus. We did this on a little bit of a larger scale. And then the PHWE methods are typically more used in industrial zones. Think food safety. What they do is they take large amounts of the food that they want, and they pretty much extract the chemical components out of it and then analyze that. Basically trying to figure out what are we eating, is it safe, should we be putting this kind of products in our food? And so researchers, have looked at the PHWE processes and started asking questions, basically trying to relate it to the more educational level. They looked at coffee machines and started asking questions, can we do the same thing except on a smaller scale? And can we do this in educational labs? And so two of the articles that I was researching this semester talked about this. One of them did experiments mostly based off of cloves. They said that cloves work really well with the extractions that they use. And they went on to say that caraway seeds can also be used using this approach. Another article said that extracting star anise or extracting shikimic acid from star anise actually works really well as well. And so we basically took them up on that. Does pressurized hot water extractions work with espresso machines and Keurig machines? We wanted to find that out for themselves, and we wanted to see if their results were actually feasible, and we wanted to see if their methods could have been improved at all. And so that's what Tyler and Marissa and I did. Marissa started out, like Tyler said, basically taking one extraction of each spice, basically proving that, yes, you can extract oils from these things. And then Tyler went on, wanted to see if there was more oil in the spices that he was using. And then my goal for this summer was to take multiple extractions of multiple spices and to see, just how much oil is in each of those extractions every time. And so the three spices that we used were cinnamon, caraway seeds, and star anise. Each of these spices had basically one main component in them. Cinnamaldehyde was the main component for cinnamon, P-anisaldehyde was the main component for star anise, and then R-carbone was the main component for caraway seeds. All of these, pretty much since these spices had just one main component, these made them more simple, and therefore more easier to extract. It's easier to extract one thing from one thing than multiple things from one thing. Things like star anise had more than one chemical component in them, but it was really, P-anisaldehyde that really showed up on a gas chromatograph. This made reading the gas chromatograph easy, and that is something that we are looking to implement into our organic chemistry labs. Organic chemistry 1 students and organic chemistry 1 and 2 students in the past have also continued research on this, and we've been able to adapt these procedures according to what Marissa and Tyler and I have found. And that's basically the whole point of why we're doing these kinds of research, like Dr. Hathaway said. We want to implement this in the classroom, and we want to make all of these procedures better. And so these next few slides are basically going to be an overview of what I did this entire summer. I'll be going through these real quick and basically telling you guys like the gist of what all of these numbers mean. So week number 1, I started out with cinnamon and a Keurig machine. Like Tyler said, getting the right consistency for these things was the most difficult thing overall, and you can see that with all of these numbers. With cinnamon, I didn't get a whole lot out. And next slide. Again, with the Keurig machine, I went ahead and moved on to caraway. I did get different extracted amounts. You can see the 250, 175, 100, and then 90. This was mostly because, again, of the consistency. I was working on getting the right, consistency for the caraway seeds. Cinnamon, when you grind it down, it gets pretty powdery. Caraway, when you grind it down, it gets pretty fluffy. And then we see later with star anise that it gets like crunchy almost. So the yields for all of these kind of show up less than 2% for all of them, and that is mostly because of the consistency. And then again with the extracted amounts, the thing with the extracted amounts is that when you get a spice too fine, it doesn't allow for the solvent to actually go through the machine and extract the spice in the first place. Yeah. And so that is the main problem that we were getting with the spices overall. Moving on to the espresso machine. The espresso machine was even more sensitive with the consistency than the Keurig machine does. I mean, with the espresso machine, there's like a pamphlet that I have to read out of reading the instructions, and there's an entire 8 points or 8 tips on how to make the best coffee based on how you grind it. So these espresso machines were very sensitive, but I was able to get a more even extracted amount as I went on using this machine. We can see We move on to caraway in my week 3. We can see that with caraway, I was able to get, finally in a measured amount of 200 every time. And then looking at these extractions overall, you can see that I was getting, for example, extraction 1, trial 1, extraction 2, trial 1. I was getting still more essential oil out from the first extraction than I was the second extraction. This basically means that there's more there. There's more oil that can be there than there would be if I only did one extraction. And then moving on to my week 4, my last week was extraction star anise with the espresso machine. Again, I have that my yields were a bit inconsistent. Again, my percent yields of 0.34%, jumping over to 1.47 just because of the consistency of the star anise. Just one, I had, pretty much just less oil coming out the second time, or the first time I did the second time. And then moving on to the very last thing I did was I used the steam distillation apparatus basically to compare my results with the espresso machine and the Keurig machine, and I found that the steam distillation apparatus pretty much distilled the most oil out of the other results that I used all summer. And so, in conclusion, these are my final results. Again, these are the average of all the extractions that I used over the summer. Basically, multiple extractions are needed to obtain the maximum yields of essential oil of every product. You can't just do one and be done, is basically what we have all learned through these 3 legs of the research. And that, again, consistent grinding of the spices is needed to get reproducible and feasible results. All of this is being worked on in the organic chemistry labs as well. This is basically like an ongoing thing. We're all learning from these, and we're all trying to improve all of these experiments this school year. I'd like to thank everyone for being here. Thank you all for listening. Thank you for having us. And this is the end of our presentation.
So now we'll take any questions if you guys have any. Yes.
I know in one of the earlier slides it mentioned TCH solvent, I think. So is TCH something you wanted to get rid of, that you were using the solvent to like extract out, or?
THF?
THF, sorry, I didn't.
Is that yours, Jordan? Right.
Professor Johnson,
So good. Right.
he goes so fast I can't take notes.
Is it THF that you said?
So,
Yeah, so what was the question again?
what are, like, is that something you're trying to get rid of, that you're using the solvent to extract away so you can have a more pure product, or like?
No, so like every type of reactions that we're doing here, like it's like a solid. So we need something that to dissolve the solid, so that we would like because we will work our reactions through like reflux. So so a reflux is like you have like this this round bottom flask, and you would put like your solvent and your solid in there, and you would just hit it and stuff, and you have like a distilling column. So it's like you need like a solvent for that. So or else like the reaction is like in solid, so it wouldn't like react with anything. So you need solvent for that. So the tetrahydrofluorine is the solvent for this case. So we have to like select different kind of solvents. Like there's a lot of type of solvents, so it really depends on what you're starting with. So in this case, we're dealing with like acrylamide, so that's like the best for this option. Yep. So you have to test different types of solvents. Yep. Any more questions? Yes.
So I think almost all three of you mentioned that there was an issue with grinding. Did you use a certain time period with the grinding, and you all used the same grinder? How did you
So
quantify
we
that?
used this one grinder that had like a fine, coarse, and like a medium one, and that one was like okay. And we couldn't get the right consistency, so then we started doing like a mortar and pestle, where you actually had to do it. And that was a pain. So then We went out and bought an actual nice grinder that has like, I think it had like 8 settings on how you could grind it. So we got a pretty good consistency, but it still wasn't completely always the same. So it was just really hard to actually get a smooth consistency that was consistent throughout everything.
And especially like for the Keurig, you know, they already come in these like pre-made pods. So they're already like at their most perfect thing. We were literally just taking like spices, grinding them, and trying to like pack them into the machine. But, I mean, these spices weren't made for a Keurig, especially. So that was like just one of the issues that we ran into a lot.
So I noticed when you used Hathaway, you had the best, or the closest to steam distillation. I was wondering with the other 2 spices, if you have any idea why those were less consistent with Hathaway.
Cinnamon would definitely have to be, I mean, I don't want to blame it on the consistency of it. It was really hit or miss, depending on how fine you got it or on how coarse you got it. Can we go to the steam station? So I can go through all of these. Okay. Yeah. And basically, it's also like emulsions. We went through a ton of emulsions with cinnamon and with star anise. Caraway yielded like literally little to none emulsions, and emulsions are pretty much 2 liquids suspended in each other, and that's what we got when we were extracting them out. And so, obviously, with steam distillation, we didn't have any emulsions simply because we were extracting with water. But with cinnamon and star anise, extracting with alcohol, it yielded a whole lot of emulsions, and we lost a lot of product over that.
One of the changes we made when you guys did it in lab is we changed the solvent to extract with the cyclohexane, and that minimized the emulsions. It still didn't get rid of them, but they were using hexane, this past spring and summer, and hexanes tend to give more emulsions than the cyclohexane. So that's just one of the changes that we made as we're going along to try to improve it for organic labs.
To break up the emulsions, we were adding like 25 grams of salt, and we put 12 grams of spice for the extractions, so it was tough to break them down.
Here's a question for all 3 of y'all. What was your favorite part of your research experience?
I like getting yields. Because after, especially with things like cinnamon that just took so long to break down and to get isolated, I would literally spend 7 hours just trying to, get everything the way it was supposed to, and then getting just like even a 2% yield just made my day every time. So yeah, that's what made me happy.
Yeah, mine would be same thing. Like you mix 2 liquids together and get a solid, you at least got something. Sometimes you don't get anything. So at least we got something.
Yeah, so for me, I think like, carrying out like those reactions is like, for me it's like cooking. Like, you're setting up like apparatus and like, you mix like different type of solvents and different type of like your starting material, and you get a final product. So it's basically like cooking. So that's my favorite part.
Lots of dishes.
Right, yeah, you have to wash a lot after that, yeah.
On that subject, how did you get the honey stuff out of your flask? Did that work?
For me, yeah. So that's a really big problem for us. So I think what we did in the end is like we reacted with like more solvent. So we dissolved that thing and we store it in the solvent, because it's just so hard to like to scrape those sticky adhesive like viscous stuff out. So yep.
Thank you guys again.
Talk to these organic chemists more. We'll be around here. Also, we'll be having lunch twice from the cafe.
Yeah. I might join you guys. Like, I don't know. I know like what kind of thing, but yeah.
PC.
Log out of this machine.
All right. Thank you for coming.